Hello, everybody. Welcome back to Every Day is Friday, the show where we dive into the stories and experiences from people from all walks of life. Today, I'm joined by Eric, a geologist who finds gold, explores Earth's hidden treasures, and we're going to talk about his discoveries and how he tracks down valuable minerals and the science behind it all. Let's dive in. Welcome to the show.
Thanks for having me, Matthew. Pleasure to be here.
No, I'm excited to have you on, Eric. Now, for the listeners who may not be familiar with your line of work yet, could you give us a quick rundown of who you are and what you do and why you do it?
Yeah, so I am a mining geologist. Right now, I'm functioning as a freelance geologist and a facilitator for possible capital investment. What that means is I try in some parts of what I do for contracts, any kind of field work that is necessary for usually smaller mining companies to explore and expand their resource at their project. And then on the other side of that, as a facilitator, I try to connect capital investment folks, funds, with those junior miners who want capital investment for a portion of their project or company. I'm fairly new to the facilitator side of things, so I'm definitely more of a freelance greenfields geologist, and I'm sure we'll get more into what that means.
Yeah, getting started in geology. I mean, what inspired you to be a geologist?
I wanted to be a scientist, but I also wanted to make money. That's the honest answer. um, it's hard to be a working geologist that doesn't just stay in research, and really just scientists in general. So geology, you have usually four main career paths. You're either going to end up in a geotechnical world, which is usually a consulting field, an environmental world, which is also usually a consulting field. And then you have oil and gas as well as the mining industries, which can be broken up into more subsets, as with all of them. But those tend to be higher salaries with just more consistent work, although you might be in more remote areas.
Now, how did you first get into studying rocks and minerals?
Uh, Really, I mean, even as a kid, when I was watching Bill Nye, I remember watching Bill Nye's pretty good for getting kids to like science. Um, there was a demonstration where he was going, "This is what plate tectonics is," and he had like syrup and pancakes on like a plate or something like that. And I remember I was like, "Oh, that was cool," but it was never something I pursued. It was just something you watched as a kid. But then I found myself, I had a little rock pebble collection from the little pebbles that are in children's playgrounds in elementary school. So I was always interested, and I just was more interested in just the natural world, science in general. And by the time I got to 17, 18 years old, I was like, okay, that's something that can transfer into a career path. So I pursued it.
Yeah, lots of kids love collecting rocks out there.
Yeah, yeah.
Now, what do geologists actually do in their day-to-day work?
So in my field, nowadays it's a lot of hiking, a lot of digging holes, a lot of finding rocks, a lot of um, writing down the data that is necessary for a company to expand their asset. Um, as far as the mining industry, which I've been involved in by far the most, there are a multitude of things you can end up doing. But you usually go down a production path or an exploration path or a data science, data management path. Um, those production teams, those are your people who are supporting the business that are in 24/7 production, and you need a geologist to manage where your materials are going. Um, let's say, as an example, for a gold mine or even a marble mine, you want to know what grade the quality of that material that you're being shipped is, and you want to send it to the right place so it can either be fast tracked to get processed or stay in one place, pile it up, and track it. So that's a lot of what those geologists end up doing. An exploration geologist, you kind of have um, some variation on what they're doing based on the project. So if you're at a mine that is going to be in production currently, you're stepping out on the property where maybe you haven't looked at it too much, and you need to use geochemical, structural, and geological data to figure out, all right, where is our money best spent? Where can I put a drill hole that's going to convert unknown material into something that we have a much better idea about where more of our resources at? And then your more data science geologists or geostatistical geologists are going to be making a lot more models or managing the data that goes into those models. So just like all sciences, you have people who are collecting data, and then people who are organizing data, and then people who are trying to model that data. So you have all these different teams of geologists who are ultimately creating a product. And with all sciences, your product is going to be a model that represents the data that you can collect with certainty.
That's great insight. I mean, most people don't realize how much goes into this job. I mean, what's your favorite part of being a geologist?
Uh, d- my definitely seeing something that nobody else has seen, and then being able to tell the story of it. Um, when you take somebody on a hike who just loves nature, but maybe they're not into the sciences or anything like that, they can appreciate it. They can love it. When you take a geologist or a biologist or even a chemist, you can kind of see the magic behind what you're seeing a little better. So when you're going on camping trips with your friends who they haven't been introduced to any of this kind of stuff. You can kind of nerd out and be like a teacher anywhere you go because you know this niche thing about something. It's like you know a secret nobody else knows about, which is cool.
Yeah, you must have been on some exciting, moments when you've realized like you came across something really cool. I mean, what is the coolest thing you ever came across while digging?
So that's kind of another fun thing that is interesting about this profession. I can't tell you. So we have a lot of NDAs, and there's stuff that you get to see at a site that you just can't talk about. Um, So, in a workaround to that question is there are things in the natural world that you can't really see at the surface because they may weather and erode. Whereas when they're locked into rock that's not interacting with much water or open air, those things can be better preserved. So you can find things like a fossil that is completely pyritized, maybe a leaf that is completely pyritized. So that means it's uh, been replaced by something that looks like fake gold. Pyrite is fool's gold.
Wow, that's incredible. Now, I mean, what's the one of the rarest rocks or minerals you ever came across outside of digging?
Um, Rarest. I mean, gold's pretty rare, but when you're at a gold mine, you see it all the time. So I guess it's relative to what you see. Um, there are, and I hope to show you some of these throughout this. There are mineral samples you can collect at different locations. In our country, you can go hike and find them if you know somebody like me who knows where to find cool stuff that you just can't find anywhere else on our country or continent. But if you happen to be driving by with a geologist, you can probably find some cool stuff. So there's just a whole bunch.
Are there any like hidden spots where people might find gold that they don't know about?
Yeah, for sure. Prospecting is still alive and well in the United States. United States and Canada for sure. Um, and really the entirety of North America. It's just some parts of Mexico you might not want to be hiking through the woods. Um, and same thing with Canada, the United States, to be fair. But it's different laws and systems set up where you can be somebody who prospects an area. And then if you find something and you want to stake a claim, you have to stake out plots of land and then you can further get permits, whatever you need to further explore that location. So there are definitely resource opportunities out there for all kinds of things.
It's very interesting. Now, like for the listeners, like that want to really like dive into what a geologist really does, and what's one tool that you couldn't live without when you're discovering, all these great minerals and rocks?
Yeah, I'm glad you asked. So I'm gonna go through some of my show and tell here. So the first one for sure is a rock hammer, and you can see how used this thing is. This is since I've started my career, this is probably my third or fourth rock hammer that's just mine for going out. Most of my career, I've used stuff provided by my companies, but the um, quintessential tool of a geologist is smashing rocks. It's breaking them so that you can see an unweathered surface and get a better look at that material. So this 100% number one geologist tool. Um, Another vital geologist tool, which I just kicked with my foot, is going to be a hand lens. So not only do you need to break it, you need to take a look. So this is the one that I just like keep in my pocket. If I'm walking around just doing my own stuff, hiking, I'm gonna have this, and you can see it is. If we can get a focus on that, it is a 10x hand lens. Sorry, I can't quite get the focus, but this is going to be something that is in every geologist's pocket. You might find rocks, you might find a hand lens, and you're gonna find a hammer around their belt. Um, and then beyond that, you have some more tools that are essential. If you're going to be in the field, I actually just bought this because my old stuff was falling apart. Um, you're going to have something like this on your belt. Now, what I have here is just a Write in the Rain book. Lots of scientists, architects are going to have this for field work. Anybody who needs to be outside working and recording data, what this one looks like blankly, you're going to have a little cheat sheet on every page, an ability to graph and write things, write scientific data, and record your thoughts. Something like this is needed if you want to record your data in any reasonable way, um, along with a somewhat specialized ruler that we use. So on here, it's going to be in uh, you got your centimeters or inches, and then you also have ways of measuring angles. Um, Essential for collecting data. If you're not carrying one of these around out in the field, you're probably missing out on a lot of stuff. And then just a pen, a pencil, and another cool little tool that I always have with me is this pen, which just looks like a pointy metal pen, but it is used to test if things are magnetic. So you're going to have maybe you're just digging through dirt, right? And you don't know what materials in that dirt. A quick check to narrow down what you got in your hand is just shove a magnet in it and see if it's magnetic. It can rule out a lot of things, give you a better idea of what's in your material. So I would say those are definitely the essentials of a geologist when he's out working.
Now, what for the listeners who may not be familiar, what is magnetic and what is not in types of things you're looking for?
Um, so there's one saying in exploration geology that gold rides iron's back, or something like that. It's iron and gold are really tightly associated, and that was something that came back in the day because a lot of the gold systems that we were mining and exploring were very closely related to iron. So if you're somewhere where you have what's called a low sulfide or high sulfide epithermal deposit or an IOCG deposit, you're very likely to be, hey, let's find iron and let's look for quartz veins, and that'll trace you towards the possibility of a nice place for gold. So that can be said for a lot of different materials, not just something that's magnetic. When you know something is nearby, you can pathfind your way to the element or resource that you're looking to extract or looking to explore for. So, iron may be a good indicator for certain gold deposits, whereas if I'm looking for a certain type of salt or a certain type of um, construction material. I might be looking for something totally different, so it might not even be useful to my deposit. So that's where the geologist comes in to understand all different types of geologists or different types of deposits and resources to understand, like, okay, I need these pathfinders. I need to understand that when I'm nearby this type of geologic phenomenon, I'm getting closer to my target, and I'm able to spend my money more effectively to explore more of that resource.
It's really interesting stuff right there. I'm sure listeners will really
Yeah.
resonate with a lot of that. Now,
Yeah.
what's a common myth about finding gold and valuable rocks that people believe?
Oh, well, I mean, biggest one for me is I love music. I love going to different bands, music festivals back in the day when I was younger and more energetic. And just I'm not a big fan of the pseudoscientific world of like, hey man, this quartz crystal is gonna just like give you good vibes and it can heal you or whatever. So just crystal healing, I would say, is the biggest myth that is totally unfounded. If it makes people happy, go for it, but I don't like it when things can potentially hurt somebody. So, somebody who's uneducated, some silly hippie, is gonna sell someone something and tell them, "Hey, man, you don't need to go to the doctor because you got this crystal, or see a psychologist because you got this crystal." That's unfortunate. So I hope that that is well known. People do it for fun, but don't take it too seriously.
Now, what's one of the biggest mistakes beginners make when they're searching for gold and rare rocks?
Um, I would say being overconfident or getting yourself into legal trouble by not understanding what's going on, who owns what. So going back to being a prospector, you can't just uh, encroach on somebody else's claim, right? If somebody else has a claim and they are actively have staked claims in an area, as a prospector, you have to respect somebody's staked claim or somebody's mineral rights, so on and so forth. Um, and a lot of these claims are in very remote areas where people think they can get away with it, which is not cool. And they do get away with it most of the time. I want to say that. But that's a good way to get yourself in a huge amount of trouble. Um, so leave it to the professionals, or consult with somebody who knows what they're doing.
That's great information right there. And I know everyone wants to know the secret to striking gold. I mean, how do you find gold in nature?
Uh, so there's a whole bunch of different deposit types. And like most sciences, it's not all completely figured out. Um, but for the most part, you do it step by step, slowly, over many, many years. Where first, let's say you know that an area is likely to have a gold deposit, or maybe there's gold deposits nearby, and your cousin's uncle owns this property and they want somebody to come check it out. First, you got to have those claims staked. You got to own the property or something along those lines. So property rights, make sure that's squared away before you do anything, before you break ground. Then you have to make sure you have the right permits to explore that area. Um, might be money, or it might be something that doesn't require a permit. Let's say that's the case, or you have all your permits. Then you're going to want to do the cheapest thing possible to confirm or deny whether you should continue to invest your capital into that exploration. So, something that's cheap is having a geologist like me come out to the property and do lithostructural mapping, right? I'm not breaking anything. I'm not um, exposing ground. I'm not affecting the water table. I'm just going out there with those yellow books and I'm recording information to figure out where might be a better place to continue to look. Um, After that, right, go, okay, this looks good. That looks like a fault or a fold system that looks like it can contain gold or has the potential to contain gold. Then you might get some soil samples in a grid. What that would mean is just dig a hole down to a certain depth that's appropriate for your soil or your area. and systematically collect samples and put them in a bag on a grid across your topography, right? That'll give you a much better idea to getting some geochemical data to figure out if we keep going down or uphill from that location due to weathering and erosion. That's where I'm getting closer and closer to my target. So even just that far, right? We've gone through some of those steps. That may take 5 years to get that far, right? You haven't even began to break ground, bring drill rigs, anything like that. Um, you're just trying to get closer and closer to where that potential resource may be. Um, and it continues along that path. There's more and more things that you can start doing. You can start taking geophysical surveys. You can start remapping now that you have a better idea of where you're looking due to the geochemical samples you have and geophysical samples you have. And then you're maybe looking at permits to drill beneath the water table if appropriate, right? And that's when you start getting bigger and bigger capital investments so that you can continue to explore your resource. If all that goes well, you have gold, you have good positive assays with high quality QA/QC, then you can really start attracting investors or start considering what you need to do to create a feasibility study to see if that resource can be extracted if everything's gone well. Um, that process is going to last several more years. You got to have a bigger and bigger team, um, and that then you're off to the races if all that goes well. I just want to emphasize that a shocking, striking amount of junior explorers never get that far. Um, it's a tough business, and you got to have the right people first, and then you have to have the right people who can find you capital second, which two very difficult things. It's very competitive.
That's great information for a lot of people out there. And there are so many amazing minerals out there. I mean, what types of rocks are you most interested in? That what type of rocks are you most interesting to you?
I like things that I can tell a story about, and things that are to somebody who knows nothing about geology, they can look at it and go, "Wow, that's cool," because I showed them that. It's kind of a joke of the folks I went camping with, or I go camping with every year. But every time we see ripple marks, which are preserved ripples, that if you've ever gone on a lake, if you've ever been near water, you can see the ripples on the shoreline, right? Sometimes those get preserved, and you can see them in rocks that are millions of years old, and you can point at it and go, "Hey, there was this lacustrine or this body of water at some point or river that preserved those ripple marks," and you can easily tell the story because it still looks like that, right? A lot of the things in geology that I may still find cool or more interesting aren't going to be as interesting to somebody who knows nothing about geology, or especially someone who's just learning about the sciences, about rocks, what they show us, what they can tell us. Um, so even though I can nerd out on it, I really, really like having something that I can explain to somebody who knows nothing about geology.
No, I feel like seeing them in person really makes a geologist come to life.
Yeah, for sure. For sure.
Can you show us some of your favorite rocks? Find?
Yeah. I got a few here. So first one is my favorite paperweight. This is something that came out of a mine. I can't disclose where, but it is a originally limestone, which we can see at the bottom here, a silty limestone that's carbon rich. So you can see how dark black and dark gray it is. And then you have another mineral, which I'm going to call calcite and dolomite, um, growing out of it. And then we can see this dark band here where you have another phase of crystal growth. And in the pockets of these crystals, you can see some that are gray or clear and some that are this goldenish brown. And that's going to be calcite with barite crystals on it. And we like to call these things nice rosettes. If this was big enough and it hadn't been broken and it was originally preserved, something like this, when it was in situ, would have been as big as this whole room that I'm in. And it would have been this giant round orb looking thing. And this is just a small piece of it, right? That happened to fall, and it was waste material that I was able to get permission to take home. So this one's super cool. You can tell a story and it looks fascinating, right? It might not be a super rare thing, um, but you can really quickly tell a story, and it's just a cool thing to look at. Um, and another quick one to get all the Michiganders that I'm sure are checking this out. I like having things from back home. This is just a nice little Petoskey stone that I also keep on my desk. So this is going to be some really ancient coral that was preserved, and it's really easy to find in Michigan, if especially after rain when you can see it really well because the water really brings it out.
No, I appreciate you sharing all that. You got any more? Or is that it?
Oh yeah, I got more. Let's see. So that calcite piece that I showed, or the multiple layers of growth of those crystals, this would be an example where you can see one as just one bigger crystal. So rather than having all these blades, you just have one bigger crystal. And the really cool thing about this one, you can see those ridges and the angles that are preserved of the crystal shape, right? It's pretty tough to get a good example of this of calcite like this big. Um, and we can see the layers of growth. Let me see if I can get this a little better here. Um, so sorry, I'm trying to highlight this. Um, kind of see how there's like bands in it, what looks like bands, and there's a darker gray, a black, and then that more milky crystal white. So that is going to be the difference between something that has a higher ratio and a lower ratio of magnesium, and that's effectively your difference between the chemical composition of dolomite and calcite. So that's pretty cool to see in just one sample, right? Um, what else we got here? What else is some cool stuff? So this is something that I really like to show or get especially young geologists or people who are new to the field or new to the working industry to check out. So there are certain angles that you look for as a geologist for how things behave under standard conditions. Now this limestone, see, it's flat. It does have some what we call bedding in it. So layers and layers of material that build up over time. Um, and then they undergo lithification, they become a rock, right? Now, sometimes that pressure can produce tension in the other directions that are not associated with compaction. So, in order for this rock to become a rock, you had to squeeze it this way, and it became a rock, right? But you have those forces, which are strongest for compaction, going up and down. That means that you have forces going outwards, perpendicular to up and down, that are weaker than the primary force, or less significant, let's say, than the primary force causing compaction. So when that happens, you create tension in those directions. So tension, like tension on a rope is going to be taut because it's being pulled in opposite directions, not because it's being squeezed by compression, right? So if you look at this rock again, see that X that's in there? Now it's that X is directly perpendicular to the direction of compaction. And that represents tension going out that way and out that way. So you have the rock getting pulled apart in perpendicular direction. And what that X is are what we call joints with vein infilling. So because this is a limestone, it's rich in calcium carbonate, and it's going to have joints that break. And because it's under pressure, those joints got almost instantaneously filled with calcite, CaCO3, because it effectively, we can think of it as the rock's material, the thing due to lowering pressure that's going to come out of the rock first, is going to crystallize within that new space that's made. That space, you can kind of think of it as like the vacuum of space, instantaneously has very low pressure and needs to be filled by something. So this calcite comes out of the rock and fills up those gaps. So this is kind of an ideal example if you are a little bit of a math nerd or fascinated by it. You can see it's like 120, 60, 120, 60, making a full 360, right? So that's just a ideal condition in which your rock is going to fracture, which is very important for young geologists to recognize and be able to see. And this also is going to tell me that this is likely joints due to compaction rather than due to some later faulting activity. So I know I got pretty nerdy on that one, but that's really cool to me.
No, it's so fascinating how rocks form.
Yeah, absolutely, absolutely, and that's what I'm talking about with telling a story. I hope I try to. Geologists have our own language, and I'm trying as best as I can not to use that language because my biggest pet peeve about scientists is that they try to talk in a way that makes them look smart rather than being able to communicate effectively with your audience. Um, and again, going back to what's my favorite thing about geology, it's showing people and teaching people, especially those who might not know as much as I do.
No, that's I appreciate you sharing all your knowledge with us. And do you have any gold there by chance?
If I did, I don't think I would want to show it to you because then people could trace down where it came from, blah blah blah, all that good
Really?
stuff.
Okay.
But well,
I have two
so
questions on gold, but you
yeah,
go for it.
well, I just want to emphasize it. It's very important to maintain your credibility as a consulting freelancer or just somebody who's working as a salary for a company. You never want to overshare materials and where they came from because maybe there's outside forces, other competitors who are trying to figure out what is at a certain site. So the coolest things that I do have, um, I don't want to put on camera because maybe that's something that a site hasn't disclosed that is on their property, and that deserves to be in a news release that they can advertise and market to their investors. It would not be appropriate for someone like me to share that with the audience.
No, I appreciate everything you're sharing with the audience and me as well. I mean, the two questions I have now are what makes gold different than any other metals, and how long does it take for gold to form in the earth?
Gotcha. So gold, um, I'll tackle the first question first. So what is gold used for? So gold ultimately is mostly used for a retention of wealth for people who want to avoid risk of having all of their investments in um, equities or in currencies that they may not have confidence in. So if you think the U.S. dollar or it is going to crash, and you want some type of retention of wealth that's in a different form of currency, gold is historically the best form of currency that has lasted through civilizations, through anything. You can always take gold and get stuff with gold. That's as true throughout time, throughout civilization as any form of currency. So to a lot of people, that means a lot. And what we're seeing right now, we had a crazy week in the stock market, and gold stayed relatively steady and is breaking 3,000, which is right around all time highs, and um, the U.S. dollar and other forms of currency aren't doing as hot. So to me, and the same can be said with crypto. Crypto's not at an all time high. Gold is. Um, so if we can get into that if you want. But that's the main use of gold, a retention of wealth, some form of security, and something that's rather unique for gold rather than any other metal is going to be that I want to say its second most uh, popular use is not a retention of wealth or it's not a technology, it's cultural reasons. So China and India both have cultural reasons to buy a lot of gold. For India, it's mostly because in the Hindu religion, there are certain events, big events in life that are important to people as they progress through life that heavily imply that you have to have gold. So those religious ceremonies require somebody to have gold, or for those who can afford it, obviously. Um, but for the most part, that's in the religion, which says a lot. And in China, there's a lot of people who invest in gold culturally. Um, from my understanding, Chinese citizens have less opportunity to invest in equity in companies, um, especially foreign companies. So their main forms of investment as an individual, to my understanding, is going to be real estate, which the government does allow and encourage, or to own assets like gold that may come in the form of jewelry. So it's become more and more popular in the last 40 years in China. Gold as a use in technology. It does have really interesting conductive properties. So you may see cool documentaries about what they're building for satellites, and you'll see these gold foil plated things. Um, and in processors, things like that, where gold has a special use case. Um, but it's definitely nothing like when you're talking about copper for use in conductivity in industry. So those are going to be your uses of gold. Now, that second question is going to be talking about how long does it take gold to develop. Gold, as well as anything that's heavier than helium or hydrogen, requires nuclear fusion to become an element that we can interact with in our world. What we're made up of, anything like that, is we're carbon based life forms. Carbon, you can say the same thing. So when a sun dies, effectively, it implodes on itself, and the heavier or the more material that sun had, the more mass it had, the heavier elements it's going to be able to fuse. So a smaller sun that collapses, maybe it can produce carbon, right? A larger and larger sun that collapses can through nuclear fusion produce heavier and heavier elements, and those eventually then blow up um, sometimes, um, and get dispersed throughout our galaxy and universe, and they eventually coalesce and a new solar system starts, and the heavier elements are going to be closer to that new star, and the lighter elements are going to be farther away. We are a planet that is relatively close to our star for its size, so we have more gold than, let's say, something that's farther out, like your gas giants like Jupiter and Saturn. Um, so all of that to say takes a long time. It's not something that our planet is going to just spit out more and more gold. It's something that requires the birth and death of entire star systems over vast amounts of time that's hard for our brains to comprehend.
No, it's absolutely fascinating. Like the nature's timeline is incredible.
Yeah.
Now,
And
are
and
there any
that's
places on the earth that are more gold than others?
yeah, for sure. Um So I currently live in northern Nevada, which is an extremely prolific gold mining district, right next to the Carlin Trend, which has an entire deposit type named after it because it's such a prolific gold deposit area called Carlin type deposit. Um, so there are conditions on our thin skin that we live on that are going to cultivate a better place for gold to deposit. So let's say you have um, an ancient ocean, or let's say we have a current ocean, right? And over time, mountain ranges continue to build up because of plate tectonics, and that ocean gets trapped. And then it starts drying out because it's no longer connected to the rest of the ocean. And over time, it just sinks and sinks and sinks. Now, water we know has salt in it in the ocean, salt water. So it's part of the water itself. So when it dries out, the water goes up into our atmosphere. The rest of the stuff that was in that water is going to slowly fall out. It's going to slowly be left behind. So all that salt gets left behind, right? The same thing can be said for any type of deposit. I used an ocean and salt because that one's easy for everybody to visualize. It just gets stuck and it dries out. The stuff is left behind, right? You probably are going to be dealing with deposit types for gold or a lot of other metals that is a little more complicated. But they all effectively have conditions that exist. And as time goes on, that deposit is going to develop because those conditions exist. And those conditions are going to be happening throughout time because of the movement of plates, the interactions they have with each other, and the conditions that that's going to allow for above and below the sea level. Um, Yeah, and that's true for any type of deposit that you're looking for. It has certain things you need to look for throughout geologic time, and then figure out if the conditions were right for what you're trying to find.
That's truly incredible. I mean, the Earth's history is like written in the rocks. I mean, how does the geologist help us understand the planet?
Uh, I would say the most fair way to answer that is that we try to model as best we can what the data represents. So, if you have a instrument that can give you the ratio between um, lead and thorium or lead and uranium. What we can do then is figure out how much lead was in this layer of rock compared to uranium versus the one that's below it and must have came before, right? So that older rock relative to the one above it, we know is older, but how much? You can compare those ratios and say, well, I know uranium decays over time. And let's say I don't even know how fast that is, but I know it decays over time. If you make enough of those measurements around the world and you get all those ratios, you can figure out not only how fast your uranium is decaying, but also what is it relative to the things that are around it. And you can say, okay, well, that rock, that material is this much older than the one next to it, right? So you can get age dates, and that's huge. Um, and different types of different elements are going to decay at different rates, and some are more appropriate depending on the level of precision you want to achieve. So let's say, all right, we've done this for a while. We have a good idea that those two layers of material are pretty young. They're relatively young. Maybe I'll use carbon then, because carbon's decay and the types of ratios I'm looking for is more precise for a shorter period of time. Whereas if I'm looking for stuff that's much older and I want to see um, much deeper in time scales, maybe I'll go back to using that lead and uranium, but it's going to be less accurate at giving me a small window of time. So think of it as the older something is, the less perfect your answer is going to be of how old it is. Whereas the younger something is, you can be a little more accurate reliably because you're using something that is going to be um, giving you a more precise answer. Um, so that is usually something that is foundational for geologists to understand. You know, how do you know the Earth is 4.6 billion years old? It's well, it takes a long time to figure out how fast something's decaying, and we didn't even have the technology to record that data for a long time. But now that we do, we can give you better and better answers, and we can try to model what that data tells us. So the best guess we have is somewhere around 4.6 billion years old for our planet, which is pretty cool. Um, yeah, I hope that's a great example, but that's pretty foundational for us geologists.
No, it's amazing to see like how much history is in the materials and minerals and rocks that we're surrounded by. I mean, now I'm just thinking here, like, how does volcanoes and earthquakes shape your line of work?
Sure. So, I guess the as a mining geologist, you have to always think about safety first. So I'll just answer it from that right away. Earthquake's important because if I'm underground looking at rocks, I want to make sure that I know my escape ways and I can do it without any lights and I can get other people who are with me to safety as well. So first things first, they're rare. But I have been underground during tectonic events. Um, I know lots of stories from guys who have been underground a lot closer than I ever was to tectonic events. Um, so that's the first thing is the safety condition. Now volcanoes, I'm not hanging out near active volcanoes that are showing signs of erupting, so no effect on me. But as far as deposits go, both earthquakes and volcanoes are going to be those things that may or may not be necessary for my deposit type. And especially when you're talking about gold, about heavier metals that are deposits, you're definitely talking about how does volcanism and let's say earthquakes, or I like to think of it as a geologist more as structure, which is this bigger envelope that includes earthquakes and faulting, but also folding and jointing and all these other things. Those are extremely vital to a geologist understanding how to find a deposit or how to describe a deposit. Um, and that's fairly universal. There's four things that geologists often use to describe rocks, especially in the mining industry. It's going to be what we call lithology, which is your description of your rock, what materials make it up, what type of rock it is. Um, your structure, which is going to be faulting, earthquakes, joints, folding, um, alterations, so the geochemical changes that have occurred to the rock since it was deposited, and minerals. So those are sometimes a product of alteration or sometimes a an indicator that the material you're looking at has some primary mineralization or some secondary or even tertiary mineralization that changed the rock and gives you further insight into your deposit. So all the last three that I named, structure, alteration, minerals, mineralization, all of those are going to be affected by the earthquakes or volcanism that occurred in the area. So it's integral in understanding the rock, the deposit, so on and so forth.
No, it's incredible information you just shared there. Now, for the listener who may not know or just not have enough knowledge on it, I mean, the Earth is always shifting. I mean, why do some areas have more earthquakes than others?
Yeah, great question. The areas that are going to have more earthquakes are going to be areas that are undergoing the most change. So, those areas that are undergoing the most change are going to be moving. So, if you have multiple plates, and let me see if I have a good way to explain this. All right, I got two books. Let's say each one represents two plates on Earth's crust. There are three main types of interactions that are going to happen to these plates. Now, they could be pulling apart, and that's going to cause the mantle below the crust to come up and deposit new rocks, usually in the middle of our oceans. The mid-Atlantic ridge, for example, you have new rock coming out from below the crust and depositing, creating new plate material. Then you can have an interaction where the plates are squeezing against each other. Now, what's going to happen here is you're going to be pushing and pushing and pushing, and you either squeeze them up together, one dives below the other one, and that inevitably is going to cause this one to kind of wedge its way up a little bit. Or you might have them sliding against each other. So, depending on which interaction you have, you're going to have more or less volcanism, right? It was pretty obvious when we're pulling it apart, you're going to have volcanics coming up, right? Not too hard to conceptualize. Now, what might be tougher to conceptualize is that when I have a plate going below the other plate, what's going to happen to the leading edge of this plate as it dives down? So it's going to get hotter, causing it to melt. The stuff that is within that plate, let's say you have more water content. Now, that water is going to become of what we call a volatile. It's going to get hotter and hotter and hotter under more intense pressure. It's going to want to escape, and it's going to want to escape up. So what happens is those volatiles interact with the upper plate, lower crust, and they're going to lower the melting pressure and temperature regime that can encourage melting. So then you have melting on the bottom of your crust, at the top of the mantle, and it's going to cause more and more volcanism. And that's going to come up, and it's going to bring with it other things that want to be with water. You're going to have metals that are then going to cling on to those volatile systems, and they're going to be transported up higher. So that's a good example of a way that you have metals that may have been in this diving plate, along with your water that becomes a volatile and is transported up. This plate gets squeezed up, and you have volcanic systems depositing more and more metals, causing more and more earthquakes, more and more volcanism. And a system like that that we can look at today, even on Google Earth, is going to be your Pacific Northwest area. We have a lot of these volcanic systems that are on the edge of that are being caused due to that diving plate. So, off the west coast of Oregon, Northern California, and Washington, you have one of these oceanic plates that's diving below the continental plate. It's melting, and you're getting volcanic systems that are pushing their way through the crust. Over time, more and more magma and volatiles are going to build up, and they're going to represent themselves on the surface as a volcano. Now, the other main type of plate interaction I didn't really get too much detail into is going to be what we call those transverse interaction. So that is two plates sliding along each other for the most part. So what happens there is you have things, you can kind of think of Play-Doh. If you've ever taken Play-Doh and almost gone in opposite directions like that, you tear it. It like peels and tears. Rather than if you just stretch it, it gets thinner and weaker. If you pull in directly opposite directions, it tears. That tearing is pretty violent compared to just pulling things apart or even squeezing them together, right? So that's usually where we find the most violent earthquakes. And that's, if again, going back to the United States, if we go south from where that plate is diving down, we get into the eastern edge of California, the western edge of Nevada, and we have these big mountains that are tearing against themselves and causing violent earthquakes. Um, so that's where you're going to see those interactions on our planet, and you can predict what type of earthquake, what type of volcanism is going to happen.
Now, what is shifting all this? Is it the magma?
So that's actually a very, very, very good question. so, um, there's a common debate of what has better evidence or if it's two phenomena that are happening simultaneously. People like to call it the plume debate, um, where you have these layers of of the earth or crust, and let's just say we have three main ones: our crust, our mantle, and our core. Core is super dense, under a bunch of pressure. It has all these metals. Your mantle, which is less dense, but uh, think of it as like plastic, super hot plastic that can morph and change, but it's not. Don't quite think of it as a solid. Um, and then you have the crust, which is this thin, really cold thing that is wrapping it up. Now, that mantle, it's not just static. It's not just doing nothing. What's likely happening, what we have evidence for, is either constant convection. So if you think of a hot tub, you pump heat into the bottom of it, and you got bubbles that circulate through the hot tub, right? Now, is that the driving force, or do you have these plumes that are tougher to predict? There's um, interactions between the chemical stratification of the planet as well as the magnetic field that make these plumes just appear in a place, and they're more likely to stay relatively stationary within the mantle. Or are both of those things happening? Probably pretty likely. Where you have convection, but you also have these plumes that are staying really stationary, and they're driving heat and new material from a lower stratified part of our planet to our crust. And a good way to visualize that is hopping on Google Earth and looking at Hawaii out in the ocean. It's very obviously a hot spot where you have continuous heat and magma being introduced to the crust from the mantle, and you can see a chain of islands that have happened over time where just the big island of Hawaii today is volcanically active. But if we go back in geologic time, the plumes stayed in the same place, the hot spot, um, where the crust was moving. So at one point, those far out islands were where that plume is, which is stationary, and then that plate moved, and the plume continued to dump more and more material to the surface as the plate moved away. And you can see that the smaller islands farther from the big island are much lower or even below the ocean, and they're no longer getting new material to them. So you can kind of get a relative time scale there of how long that hot spot, that plume, has been dumping material to the surface. Um, so yeah, that's actually a very there's still lots of active research going on convection and plumes, um, and describing them as technology develops and we're able to figure out more.
I'm just thinking here, could the moon have anything to do with any type of things moving on the Earth's under the Earth? You know, it's changing a lot of stuff that we're on the surface of the Earth.
Sure. And uh, so a couple things with the moon that are really cool, really good anecdotes. The moon, big mass of material out there, right? It's going to affect how tides function, right? So you have this big body out there, and the moon is tightly locked with us as we spin around and it follows. So the tide doesn't actually bulge out directly on the moon. It's a little in front of where the moon is, and it's trying to catch back up to the moon because that's where it's getting pulled constantly. So that's mostly how the tide actually functions. A lot of people think it's just like reaching out to the moon. It is, but in reality, the moon is slowing down how fast we're spinning, which is really, really cool. The Earth spins a certain speed, and the moon, because of how it's interacting with the Earth, how it's locked in its motion, is slowing down our spin. So, because it's slowing down our spin, it's going to slowly over time affect our field of gravity, the convection of the mantle. It's going to have this cascading effect of how our planet behaves, um, far beyond the tides. So, yeah, it's really cool. The moon's a big deal.
No, indeed it is. And I'm just thinking of like I know a lot of people love collecting beautiful stones out there, and I mean, what do like gemstones and crystals have in common with gold?
I mean, they're really nice to look at. they're can be valuable depending on what you're getting. But for the most part, we have to think of what is their function in society, how are they used. Gold is definitely used as a fashion statement or as a cultural piece, where gemstones are as well. Now, if we go back to earlier, that's not big chunk of what gold gets used for. It's mostly used as this financial safety net, right? Gemstones, not so much. Gemstones are something that's going to be used by extremely fanciful people that just want to own some thing that's probably going to depreciate in value. There's a lot less industrial use for most gemstones, so they're just not going to be as valuable. Um, and you can even think of diamonds, right? It's probably the one that gets used mostly, and it's culturally relevant anywhere where you have uh, people who have integrated it into their religious or cultural practices. So in the Western world, that's very common for folks who or societies who come from a Judeo-Christian background that latched onto this idea that you have to have a diamond for your wedding. Um, but for the most part, most gemstones uh, don't have that big of a market. So they're not going to be behaving the same as gold. I would say they have more not in common with gold.
Now, how are most gemstones formed?
It's most gemstones are going to be in your granitoids, your large granitoids, which are um, silicic rocks. So we can think of it as having two different types of igneous rocks. It's either going to have more stuff that is denser and heavier, or more stuff that is less dense and less heavy. So those silicic rocks, um, are going to preferentially cool later in the cooling process when the heavier stuff is already solidified, and then you have the lighter stuff um, that is going to maybe take longer to cool because of the chemical composition. Those are going to create bigger and bigger crystals in the rock. The longer it takes to cool, the more time the crystal has to grow. Whereas if you flash cool something, you're going to have something like obsidian. We can call it volcanic glass. The crystals are tiny. You can't really even see them with the naked eye. Where when something takes a long time to cool, you're going to get big crystals, and they're likely going to be some type of granitoid. Um, then you can go further into the chemical composition of that granitoid, and some of those crystals might be something that is a gemstone that people find value in. So that's, in general, that's how you get a lot of our gemstones that people may collect.
No, it's very interesting. And maybe you can or cannot answer this question I have for you. But I mean, what happens after you find gold? And then what happens to a gold mine after you're done finding all the gold there?
Yeah. So when you find the gold, you either are in a stage of exploration, planning, extraction, or exploitation of the resource, and then your remediation and your recovery of the location where you exploited the resource. So that goes with promises you've made through permitting systems to the government, to the state, to the federal government, rather, to the state, um, and to the local communities, where you say, hey, I'm going to extract this resource. And when I'm done, I'm going to do these things to ensure that our environment is safe, our community is safe, it brings value to everybody, and it's going to be a good investment for everybody all around, right? So you effectively promise what you're going to do before you do it. And that's how it works nowadays. Back in the day, 100 years ago, it was very different. There was uh, maybe not so great practices happening in North America. Today in North America, mining is totally different. So we remediate when we're done mining. Um, and depending on your deposit, depending on the chemicals that are in that deposit, you have to do different stuff. So I don't want to put too much of a blanket term on what exactly is going to happen, but you got to clean it up. Let's just say that you got to clean up what you have done to the land.
Now, what is the difference between modern mining and the old gold rush method?
Sure. So the biggest difference back in the day when the gold rush was happening in the Western United States, the California gold rush especially, um, which created San Francisco. If anyone tells you any different, you can remind them San Francisco's a mining town. Don't forget it. Um, what they would do because of the types of gold that they had, it was just what we might call free gold, where you just pick it up out of the ground, just got a chunk of gold if you can get it loose. So what they would do is make a dam, let's say a few miles away, um, and then dig some trenches and divert an entire river system, and then pump the water into the mountainside and just wash away everything, and then filter it all and just collect all the gold. That was extremely destructive to the countryside, as you can imagine. It just like washed away a lot of the mountains. And that the Romans did that in Europe as well. Um, and that was pretty common, basically up until um, I don't know, the early 20th century. And then it drastically changed because of the damage it caused to the communities, to the environment. We went, maybe that's a bad idea. Let's figure out a better way to do this more safely, and not destroy the other natural resources in the area. Uh, Obviously, the water system. the soil that you need to grow crops, um, and just the land that is used by the entire biome. So we don't do things like that today. Today, if we want to mine somewhere, we have to catalog, all the wildlife that's there, how close we are to the water table, um, how we're going to ensure we're not interacting with it, introducing things that are going to damage the nearby community. There's just so much more that we have to do today, not just the water and the land, but also the air. So, what chemicals, if any, are you introducing to the air, which causes more capital investment into processing facilities, into making sure there's no dust in the air, right? There's just so much more that we do today that 150 years ago, people probably weren't even thinking of. So, a lot has changed.
Yeah, the way people search for gold has changed a lot.
Oh, yeah. Oh, yeah.
Now, you did mention it. I mean, is mining bad for the environment?
I would say it's a net positive to mine. If you can't grow it, you have to mine it. So if you want to have green technologies, you have to mine. There's you can't avoid that. Do you want metals that you can use to create electric vehicles, that you can use to keep the lights on, to do whatever? There is a deal we have to make as an educated society, hopefully educated society with filled with critical thinking, where you have to say, can I extract this resource that we need as safely as possible, as responsibly as possible, so that we can develop technologies and build products that our society needs? So I would say the best way to answer that is is a certain plot of land going to be better off because you mined there? Probably not, right? That's fair. That's being honest. Is it something that our society requires to make the rest of our lands a better place to live, a better place to have food and lights and all the other things we need for our society to run? I mean, even the technology to develop our food, to make sure that our water is clean. You're going to have to mine to develop those technologies, right? So I think it results in a net positive to extract resources, to make products, to make our society a better place to live. And that ultimately is going to affect our environment as a whole. I like to think of society, country, our people as people who work together to raise our standard of living higher and higher, have a more responsible governance of our natural resources over time by developing technology, developing human capital. Um, and in that way of looking at it, you just have to mine. So, sorry for the long winded, very biased towards the mining industry answer, but I think that's the best way to look at it.
No, that's very good information for a lot of people out there. And I mean, there are so many interesting locations on Earth. I mean, if you could explore any place in the world for geology, I mean, where would you be?
Oh, selfishly, I mean, well, I'm in Nevada. I've worked in the mining industry in Nevada and Arizona. They're probably the best place for me. I'm an American. I don't have to travel to another country. There's a lot of work here, and it's not miserably cold like it is up in Canada and Alaska. Um, and I'm in my country. I'm relatively close to friends and family, um, and there's a lot of opportunity to do something here. So I think I've found myself in the best place.
Now, are there some good places in Africa and maybe Brazil or India?
Sure, sure. There's opportunities anywhere where you can get value. Um, Whether or not I would personally like to go there, that's a whole nother question, right? Um, yes, there are great opportunities other places in the world, but I think right now with what's happening, especially in the last few weeks, um, with people not confident how this tariff trade war is going to resolve itself, it's very likely that we're going to end up extracting more and more resources within the United States for companies within the United States to develop their products. It seems to be looking that way. So I don't see the reason right now to be driving to go to places in Africa where I want to say the vast majority of foreign investment might be coming from China. Same thing in South America. The United States and other Western governments used to be leaders there, but it's just not true anymore. China's doing an excellent job of investing in foreign resources. And I think with this new administration coming in, um, they have realized that as well. I think the previous administration did too, but now it's being publicized where we're trying really hard to make deals for the exploitation of resources in other countries and to have better deals to be able to make those trades for the resources that we can't exploit here yet. Um, but I do think we're pushing in a direction where we're going to try to do everything in house.
Now, do you think other countries, like I mentioned just a couple of countries, I mean, are they all doing the same thing as we're doing here in the United States for finding gold, like Russia, I mean, China, I mean, India, I mean, all these big countries out there, do they have the similar operations as us?
Well, China and Russia definitely do. They have massive deposits. And the scale is is tough to talk about. Just because whatever's not publicly available, I'm not going to be familiar with, or if I am familiar with it, I don't want to share it. It's on shaky ground there. But there are big deposits. But the thing about big deposits is you always want the next one. If you have a deposit that's going to last you 30 years, I don't want to just chill out and like, all right, I have enough, let's say, copper for 30 years. Well, if you know that a mine takes, let's say, 20 years from the discovery to even get going, if it's really good, I need to be constantly looking for new ones that I am heavily invested in, I have big equity in, and I have a good deal going with that country to make sure it's a consistent thing that I can get my hands on. Um, I think that China's done a better job than the United States or other Western governments in ensuring that their pipeline of resource is going to continue to come in for the next half century. So we have catching up to do. Not on everything, but on a lot of things that matter a lot. Um, Rare earth elements, copper, tin, aluminum, I think is still definitely in that category. Probably iron as well, um, which is a big deal. So we got some catching up to do.
No, definitely. I think there's a lot of minerals and rocks all around the world. Just saying what you're saying, and now there's always like a fun fact about certain rocks that surprise people. I mean, what's one thing about rocks that most people don't know?
Uh, they're really old. I mean, most people don't even think. I mean, most people know that, but I found um, really understanding geologic time is an easy thing to talk about, but a hard thing to really conceptualize. A good way to think of it is everyone remembers when they got to that math class where they just weren't having fun anymore. Their heads started to hurt, and it was like, man, I feel like I worked out the muscles in my brain, and I don't know if I enjoy that right now, right? So it's not so much um, that it's difficult to grasp. It's that you have to work at it and be familiar with it a whole bunch. So that the idea of geologic time and how it pertains to any rock you can pick up in your hand um, is very vital to understanding um, geology as well as just the world of natural science. Um, so if there's anything that I hope somebody does when they pick up a rock, it's I wonder how old this thing is, right? And then maybe taking a look at a geologic map and going, wow, that's 120 million years old, and there were these critters running around when this rock got deposited. Because then it just leads down the rabbit hole of cool stuff you can have fun with, rather than just study and make your head hurt and try to stress out about it. Just have fun with it, um, and just think about how old it is. To me, that's a good time.
Now, as a geologist, have you ever thought about exploring like other planets or rocks or meteors for the rocks?
Oh, I mean, I've thought about it, but I'm not that. Usually, you got to be somewhere in the PhD land, very invested in research, um, to start thinking about getting employed as a uh, astrogeologist. Um, it's very niche. Not many people are doing that for sure. A mining geologist is already really niche. Those folks are very, very niche. There's not many of them, and that would have, I didn't even mention it when I was talking about the main fields that geologists work in, because it's just something that is it requires a lot of dedication. You're likely not going to be financially compensated on the level. You got to be extremely passionate. So, have I watched documentaries, read papers, read books about it? Sure. Um, have I thought about doing that as a career? No.
But it's very interesting because there's people out there that are actually trying to understand the science behind all these. So it's mostly meteors instead of other planets, correct?
Um, I mean, I guess. What do you mean by that? What is mostly meteors?
I saw one thing that said that they were going to find all these minerals on meteors and all this gold, and it's just going to make our gold prices just completely just change the game of our gold prices and stuff like that. And you got to really understand the amount of science that has to go into it, the money that goes into it, and even how to get it back here to the planet Earth.
Yeah. So before I get into this one, I want to emphasize I am not a financial advisor in any way. People can invest in whatever they want to invest in. I would just be wary about people who are social figures who are trying to get you to look at a company that is talking about a technology that doesn't exist yet. Um, so let's just do some simple thought exercise. Right now on our planet, we have plenty of, let's say, gold deposits where we know where they are. There's not enough gold to make it economically viable to mine it, and that's on our planet, on our surface, right? Think about how much more expensive gold has to be to make it profitable to have a couple $1 billion rocket ship that has a payload of, let's just make up a fantastical number just because we can. Let's say it has a payload of 10,000 tons that it can bring back from a meteor. So not only does it have to get to a meteor, it can take 10,000 tons of material and bring it back to Earth. Now, just that alone, you are now 10,000 tons heavier re entering our atmosphere. That's a problem. You're probably going to explode and just throw a bunch of rocks into the atmosphere that's going to burn up, and everyone who's on that vehicle is going to die. So that's probably what's going to happen. Um, then you have the issue of, well, yeah, let's not do that. Instead, let's go to a place, mine, process it, then bring it back. We'll already have the product when we bring it back. So you're going to make a 10 on our planet. It costs, let's say, $3 billion to make a new processing facility for uh, a deposit to be mined. You're going to make that in space and then bring stuff back. That's just silly talk. It's so much silly talk, and there's so many holes you can poke in it. What's the reality is when we become a spacefaring civilization, we need to develop the technology so we can go into space, mine the stuff we need, and then use it in space. That's something that we can talk about happening later in time. I haven't talked to anyone who's serious about mineral extraction that's going to be able to mine stuff, bring it back, process it here, and then prove that that's safe and profitable. I haven't seen anything at all that comes remotely close to something that sounds realistic. So that's one man's opinion. Again, I'm not giving financial advice. I'm just saying there's so many science and engineering problems that um, just don't seem like they're in our near future.
No, I appreciate your insight on that. And it seems like we got a lot of stuff here on the planet Earth that we don't have to go out there and
Yeah.
discover a lot more minerals and rocks and stuff like that. I mean, you gave some great tips. I mean, now, what advice would you give to someone that wants to become a geologist?
Look at as many rocks as possible and become truly passionate about being an outdoorsman. Um, and you have to love it. With anything, you should love what you're doing. Um, with geology, a lot of the field work I do now um, is hiking. You know, I've had some 5,000 foot elevation days in the field, a 12-hour day where I'm hiking around, digging holes. I got 50 pounds on my back. Um, and I love it. You know, if that doesn't sound something like you ever want to do in your life, or you just don't like being outside, it's probably not for you. Um, if you, a kind of funny joke is you have three kinds of geologists: an IPA geologist, a Scotch geologist, and a boring geologist. We're kind of a special crowd. We're outdoorsmen who like drinking for the most part, and we like talking about science. Um, so if you're passionate, you like all those things. Not everybody is into drinking, but most geologists are pretty fun, cool to be around, and they're the kind of person you might see hanging out, camping in a pretty remote place. Um, and they're passionate. We have a lot of entrepreneur types in geology. Um, so just read as much as you can, look at as many rocks as you can, and go outside.
No, it's great tips for someone that wants to get started. I mean, what's the best way for a beginner to start learning about geology? Is it just go out there and study the land?
Yeah, just go outside, pick up a rock, and figure out what it is. Just, that's the best answer for sure. Is I'm more and more somebody who leads into the idea that you can put somebody in a classroom for 100 hours and just drill them on a textbook. But I'd rather have you have 20 hours of experience of picking up rocks, finding the book, trying to identify the things we use to describe rocks, and just do it yourself. Just grind it out. Just figure out what's in that. I can identify what this crystal should be based on the color, the streak, blah blah blah, all these things that we use to describe the rock. Just do that for 20 hours. You're probably better off than sitting in a lecture and talking to somebody who's been in research their whole life and um may or may not even have uh that much hands-on experience. I think the best professors out there are people who were in industry and then came back to being a professor because they wanted to share their passion with people. Um, so just look at more rocks. Just try to figure out what they are.
No, thank you for sharing that. I mean, there's always something new to discover. I know that. I mean, what's next for you in your journey in geology?
Oh, who knows? I want to. I've been in gold, copper, and silver. the entire time I've been a geologist in the mining industry. So I would like to get more and more experience in things that I don't have an expertise in, work my way towards professional licensure. Nevada actually doesn't have a good, not the best system of getting a professional licensure. So I'd like to go to a state where it's easier to do that and it's more valuable to my career path. And to justify that, I want to work with more types of deposits. So it's just what I was saying a moment ago. I want to look at more rocks that are different than the ones that I've seen before.
No, I love that. And, keep chasing your dreams because your dreams won't chase you. I mean, where can people follow your work and learn more about geology?
Honestly, you can um find me on LinkedIn. So Eric Sattler on LinkedIn. And if you want to reach out, talk to me about geology, talk to me about my experience, how to get into being a geologist, or if you happen to be a investment fund looking to find uh, junior miners that fit what you want in your portfolio, I might be able to facilitate some meetings. So I would say LinkedIn is probably the best place to follow.
And your information will be in the description down below. Eric, this was an incredible conversation. You're passionate about geology and finding gold is inspiring, really. Thank you.
Yeah, no problem. Anytime, Matthew. I appreciate you
Yeah,
having me
no,
on.
no, no, thank you for sharing your knowledge and your stories with us. I really do appreciate it.
Yeah, it's my pleasure.
And for the listeners, stay tuned for more stories on Every Day is Friday Podcast 365. Until next time, everybody.